We have seen that the plasticity theory allows us to explain very elegantly what is called the brittle to ductile transition, and that is the transition of a material to fail upon deviatoric loading from a brittle failure to a ductile failure, which specifically in the plasticity theory we have seen that this is called strain softening and strain hardening. And for the same material, you can go from strain softening to strain hardening just by increasing the mean stress or the least principal stress, or also the parameter P prime that we have seen in in the Camp Clay model, which is the parameter used to show the mean stress. Here I have an example of a photo taken. I'm not sure. A friend of mine sent me this, and I'm not sure if it was in the museum, the New York Museum of Natural History, or it was in the Smithsonian Museum. If some of you lives around there and wants to check out these rocks and tell me where those are, please tell me so I find the reference. And you can see in these rocks how that transition takes place from low confining to increasing confining pressure or mean effective stress. And what we can see is that as the mean stress increases, the way that the rocks fail changes significantly. Here we have strain localization. As we move forward with higher mean stress, we have distributed failure in the sample. And this is very important because this can explain the deformation and failures of rocks at a high depth. Most time we're used to think about rock failure in terms of ambient conditions, low pressure, low temperature, but at significant depths, that's not what that happens, and it might be significantly different to what we have on surface. Okay, the mean stress is one of the factors that can cause this brittle to ductile transition. There are some other causes that can cause this same type of transition. And here, and let me show I have two examples. The first one is just with increase of mean stress. And here you have actual data. Is not the same rock, but I guess it would be pretty similar because this also looks like a marble. And here we have a plot from the book of Jagger, in which we have this transition from brittle to ductile with increasing least principal stress sigma 3 in triaxial test. So just to complete this figure, what we're seeing here is what is the sigma 1 minus sigma 3 required when we have an effective confining stress equal to sigma 3, where sigma 2 is equal to sigma 3. And you can see very nicely this transition and how it goes from being a brittle material that fails right away as soon as it reaches a peak stress to being a ductile material that can resist quite a large stress without localizing a fracture and without failing abruptly. Okay, as I was telling you, we have or we know about other variables that enable this transition from brittle to ductile. And probably the one that is the easiest to see is temperature. And we see something similar, that with increasing temperature, we see a transition from brittle failure to ductile failure. Notice in this case, the strength of the rock is decreasing with increasing temperature and decreasing as you go from brittle to ductile. It's the opposite of what we have here on top. But the transition from brittle to ductile is observed. And this has a very important meaning in terms of engineering and geological applications, because the deeper you go, the higher the temperature and the higher the confining pressure or mean stress is going to be. And you can combine these two parameters as we see in this plot, where as we go deeper, we go into higher confining pressure or higher mean stress and higher temperature. And here we see two examples. We have dealt mostly in our plastic analysis with compression, but you can also have a similar transition, brittle to ductile, also in extension. And what we see over here is that, for example, for this particular limestone, there is a limit of going from brittle to ductile of a confining pressure or stress of about 100 megapascals, and that's already several kilometers of depth. And also there is a transition which depends on temperature, and mostly above, for example, 500 degrees. No matter what is your confining pressure, the rock is going to fail in with a ductile type of failure. All right, so mean stress and temperature are the main parameters that control this brittle to ductile transition. But I'll also like to share with you a few other factors that can also affect this brittle to ductile transition. And let me make the summary here. So we summarize all the data and all the phenomena. Brittle to ductile transition in rocks. And we have seen that we're going to favor this brittle to ductile transition, we said, as we increase the mean stress. And this is P prime in the PQ space. And it's the same as saying increasing the effective least stress or the minimum principal stress. We also say that this transition is going to be favored with increasing temperature. Let me just clarify here. This is temperature. This is mean stress. The transition from brittle to ductile also is going to be favored by decreasing the loading rate. And what that means is that as you lower the loading rate, for example, at geological times, the deformation of 1% in a million years, the material is going to have the time to accommodate internal failure and appear in that period of time as if it were in a ductile failure instead of a brittle failure. If you load the same material very quickly, most likely it's not going to have that time to reaccommodate internally and may develop a brittle failure. So loading rate is also important. And another factor is also mineralogy. Rocks made out of different types of minerals are going to have a different type of brittle to ductile transition. And in this case, let me just refer to the case of rocks. We have seen that with sediments, uncemented sediments, like uncemented sands or mud rocks without significant cementation, we can see this brittle to ductile transition. But let's say now for a cemented rock, what could affect brittle to ductile transition? And that's going to be mineralogy. For example, in organic shales, there are several studies that show that as you increase the total organic content in a shale, or let me say, you're not increasing it, the total organic content, but as the shales that have a higher organic content usually display a higher ductile behavior. And as you increase also the amount of clay, the ductile behavior is enhanced. These two types of components, organic matter and clay, tend to have a more ductile behavior than, for example, quartz or carbonates. That's why, for example, a dolomite tends to be a very brittle rock, or for example, a tight sandstone made just out of quartz also tends to be brittle. But a shale with high organic content and high amount of clay would tend to have a more ductile failure than a rock with a much lower component of these two. And there is one more type of phenomenon that I like to share with you, which is often disregarded, and which is, and to me is very important, is just all right, and this is length scale. And let me use a schematic in order to explain this phenomenon. Let's imagine that we have a rock mass which is naturally fractured. Almost all rock masses are naturally fractured at some scale, and will exhibit these fractures that may be at a shorter, at a longer distance, but almost always we're going to have some of these natural fractures. If not, you may even go at a higher scale and think about faults. All right, we can test within this rock mass, for example, a piece of intact rock somewhere over here with a small size, let's call it L. And if we were to run a triaxial test on that particular sample, what we are going to observe is that if, let's imagine this is a rock mass made out of a brittle rock, then a piece within the intact rock is also going to be brittle, and it may show a response that, let me show us in a schematic, something like this, where soon after the peak, the rock is going to fail, and this is going to be brittle. All right, we can go to the same rock mass, but let's say that now we can obtain a much larger sample. And this time, instead of testing the intact rock, now we're able to sample a rock mass with fractures inside, now with a length L. And again, we take this to a large triaxial cell and we fail it. What are we going to see in this case? What we're going to see in this case is that my sample is not going to depend, the strength is not going to depend only on the strength of the intact rock inside, but also on the fractures inside the rock. And therefore, you should not expect to reach the same strength of the intact rock because this one has fractures. But not only that, the strength is going to be lower, the stiffness is also going to be lower because of the presence of the fractures, but also the material is going to behave in more a ductile manner. Why? Because now, as you are failing the rock, you're actually mobilizing the frictional strength of the fractures. So in the previous case, if this is a sample of size L, when you break it, you create new fractures in the rock. However, in this other sample, which is a bigger one, when you get to the maximum strength, you're going to be mobilizing the internal strength of the internal fractures. And you may also break the rock matrix inside, but first you're going to mobilize the internal fractures and the strength of the internal fractures, so that when this material now fails, basically what you're going to do is, if we're loading in this direction, then this side is going to go down with respect to this one, and this one is going to go down too, and probably this one could go up with respect to this one, and so on. But at the end of the day, this will look like loading a rock along surfaces and obtaining the frictional strength mostly. And that also will look more ductile. And this is something that is very important to recognize, because many times we model processes at the larger scale with the properties of intact rocks and properties that we measure in the laboratory, and then probably we get this answer for the laboratory. But in reality, if we want to model a large rock of mass, we have something similar to what we have over here, and not to what we test in the laboratory. And the same rock, but sample at different scales, including internal defects, like such as natural fractures, can show quite different in a shear failure mode. All right, let me see if I forget anything. I don't think so for this part. Let me just continue, and let me just complete this drawing. So where L is much smaller than L. All right, and there is one more thing that I'd like to share with you, and this is also linked to brittle and ductile transition. In this brittle to ductile transition that we have seen with mean stress, with temperature, with mineralogy, with change of length scale, we have often assumed that there is something which is called an isotropic hardening. And what that means is that the yield surface changes in all directions the same way. For example, if we were to plot the principal stress space with sigma 1, sigma 2, and sigma 3, and a hydrostatic axis going over here, and let's say I have a yield surface which looks more or less like this. Try to imagine that in 3 dimensions. Isotropic hardening means that the yield surface is going to grow the same in all directions. And as the material gets stronger, for example, the yield surface is going to change in all material directions. And this is a big assumption, and sometimes it's not true. So that's why it is important to recognize that. In our previous modified Campbell model, we assumed isotropy, and because of isotropy, also we implicitly assume this isotropic hardening. Sometimes this is not the case, and instead what we have is something called kinematic hardening. We talked a little bit about the Kayenta model in previous lectures, and the Kayenta model is it's a model that can capture this kinematic hardening. Basically, in kinematic hardening, the yield surface is going to grow or move in a direction which is not the same for all the principal stresses. For example, I could have a yield surface similar to the one I had before around the hydrostatic axis, but if I were to fail the material in a particular direction, I may, you could say, anneal some of these yield planes, so that when they fail again, actually they get stronger, or they just get stronger in one direction. And because of that, now the new yield surface may be somewhere over here off the hydrostatic axis. And this type of hardening is not isotropic anymore. Something similar to this is what happens, for example, in a compaction band. In a compaction band, you tend to get a material a lot more compact in one specific plane, specific orientations, so that the material gets stronger in that specific orientation. And you could have something similar also for, instead of hardening, for a weakening of the yield surface, in which the creation of fractures also might weaken the material in a particular orientation and not in all of them, as we usually assume with the isotropic hardening. And one more phenomenon that I like to share with you is the phenomenon of chemoplasticity. You remember that we talked before about chemoelasticity, and we said that changes in chemical potential in the fluid or in the rock can cause deformations. Sometimes also changes in the chemical potential in the fluids, in the rocks, could cause, for example, dissolution of some of the minerals within the rock. And that, of course, is an irreversible process, and it's going to cause a change of the yield surface. So let's think in terms of the PQ space, and let's say that now we have a cemented rock. So the cemented rock has a yield surface which has a tension cutoff and has a given shear strength at P equal to 0. So by the action of chemoplasticity, let me make this a little bit bigger. By the action of chemoplasticity, what I can have is a reduction of the yield surface due to a chemical action. And in this case, I'm assuming that the chemical action is lowering the yield surface, but sometimes it could be the opposite, right? If you have the precipitation of a cement on, let's say, a fracture, then you're going to be increasing the yield surface on a given direction. Examples of decrease of the yield surface with chemical reactions, notice that we are lowering both the pre-consolidation stress, the tension cutoff, all of them are lowered by this chemical action. Example of these is the case of mineral dissolution. When we have a carbonate rock and we perform acidizing, the porosity of the rock gets larger, and also the strength decreases and the stiffness decreases too. Another example is hydrate-bearing sediments. Hydrate-bearing sediments usually have these ice-like structures that are called hydrates, and that upon depressurization, that solid hydrate can disappear and cannot contribute anymore to the strength and the stiffness of the sediment. So after that change, I have a new material which is weaker than what I had before. And in order to solve these problems, you need to consider these effects and goes into the field of chemoplasticity.